So Dr. Kogi, his life work essentially for the last 30 years in the background, as he's done a million other things, has been dealing with what he sees as a wall. And a wall is what you have when you need a new architecture. And the idea is this. There's an important class of applications, mathematics, that we need to do real fast on an architecture. And we can't get more performance with the existing trends. An example of this, the first wall that he likes to talk about was in the mid-90s. And what happened here was, remember that picture I showed with the core clock speed? Cores got faster and faster and faster. Well, what happens, remember I talked about how we need to access memory. You couldn't access memory fast enough to keep the cores busy. So you had an imbalance in your architecture, and what was happening was, even though clock speeds were going up, your performance on your algorithms was sort of leveling off because you couldn't keep it up with the processor from the memory. So how do we deal with that? Well, we had a paradigm shift. That we went to these. That's when we went to these big caches, and that was a huge architectural advance. It involved rethinking how we build these things. It was a new paradigm. And then the second wall in around the mid-2000s was what he calls the power wall. And the idea here is, with the caching solution, we could keep increasing the clock speed. Clock speed kept going up, cores got faster and faster. Then the thing heats up, and then you have to deal with cooling it. And that's when you run into the second wall, which is the power wall. And that meant we had to think things through again and do something differently. And the solution there, that's about when we went to parallelism. Lots of small cores on a chip. Instead of building these really complicated cores that do lots of things, we'll slow them down a little bit and have lots of them on a chip. And they're simpler. We can run them more slowly. Therefore, we use less power. We don't have to worry about cooling them. So that was the second wall. Dr. Kogi's argument is that we are right now in the middle of a wall, and that wall he's calling the locality wall. And the idea here is that we have a new class of applications, and I'm going to talk about what they are, and some of them you may already know, with really, really high memory bandwidth requirements, with really, really high messaging costs, and we call those memory-intensive applications, and they simply don't work with the architectures that we have today. And I'm going to tell you a little bit about why. So what do we mean by memory intensive? So when I talked about the efficiency of the architecture, I talked about operations, how you want to keep those cores busy doing operations. The problem with this class of applications is it's not dominated by operations. There's actually more memory accesses in operations in the algorithm itself, and that causes a problem for these architectures. There are large, we know about big data. The data is big. There's lots and lots of it. And you don't always reuse it. Remember I talked about caches, how you bring a big a pot of something into the local memory and you reuse it. Well, in these algorithms, there isn't always reuse. So what do we do with that caching architecture that we built around this idea of reuse when we have algorithms that don't exhibit that behavior anymore? So that's one another thing. Regularity. The dense matrix multiply that I showed is very regular. I'm sequencing through a vector of elements in a very predictable way. I can pre-process it. I can design libraries to do it very efficiently. It's very predictable. But today's applications process things like graphs. I don't know if you guys have worked on graph algorithms or sparse matrix algorithms or statistical methods. They don't have that regularity. You can't predict what parts of memory you're going to access from one step to the next. So that's another feature of these applications that's causing us problems. And then finally, in the context of all this, we have to worry about streaming. A lot of these databases are in real time. You're getting new data. New web pages are cropping up, or new people are joining your social network, and you need to incorporate that data into your data set. So you need to worry about that stream of data that's coming in as your algorithm is running. So the point of all this is that the locality that we've come to expect from applications is going away, and that's causing problems for our architectures.